Right, this is Level 2 Physics from this year's exam. Demonstrate understanding of electricity and magnetism. So just be warned, it looks like I'm only going to be able to do the first two questions, two or three of these questions, because the third one is blanked out. So I'm going to be using this formula sheet here with its equations and constants, most notably these formulae right here. So with that said, let's do it to it. So the first question says that an inkjet printer uses voltage across parallel plates to aim electrically charged ink droplets at the paper. The plates are 1 millimeter apart. Okay. So 1 millimeter apart is 1 millimeter is 10 to the negative 3 meters. So we need everything in meters, not parts of meters. And we don't know what this thing looks like. Could look like a stick man for all we know. Okay, draw the field lines between the electric plates and the charge on the top plate. So if the bottom plate is positive, the top plate must be negative. And the charges are going from positive to negative by convention. And as long as they're evenly spaced, I guess you could have maybe them going out on the outside, but not really. But as long as you have them in the middle here going straight up and down, you're fine. Okay, calculate the voltage across the plates when an ink droplet with a charge of, this is just the Millikan experiment, isn't it? With a droplet with a charge of 4.80 times 10 to the negative 10 coulombs. So the test charge is 4.80 times 10 to the negative 10, is subjected to a force 9.60 times 10 to the negative 4 newtons. Calculate the voltage across the plates and the distance. With the force is that we really need to link some way from the charge, the force. Oh, the other thing we've got is the distance. So the distance is 1.0 times 10 to the negative 3. That's a millimeter. I don't think there's one that goes straight there. So we need to find the electric field strength. So that's going to be the force divided by that charge. So that's going to be 9.6 times 10 to the negative 4 over 4.8 times 10 to the negative, what did I say before, 10. And I've no idea how to do that off the top of my head, so let's grab our calculator. Okay, 9.6 E minus 4 divided by 4.8 E to the minus 10 is 1, 2, 3, 4, 5, 6. So 2 million somethings. Okay, and now that we've done that, we can find voltage, because voltage is given as the electric field strength times the area times the distance, which is, I'm going to say, 2 times 10 to the power of 6 times 1.0 times 10 to the power of negative 3. And it's going to be 2 times 10 to the power of 3, which is 2000 volts. And that's how that's done. Right, the next question deals with velocity by the looks of it. So the voltage across the plates is changed to 4,000 volts. Wow, 4,000 volts. And a droplet of mass 1.02 times 10 to the negative 11 kilograms carrying 4.0 times 10 to the 9 excess electrons is released from the negative plate. Calculate its velocity as it reaches the positive plate. Wow, okay. Right. This is essentially a Millikan experiment. So let's do it to it. So let's work out what we've got. We've got the big V is 4,000. The distance is 1.0 times 10 to the negative 3, although I don't think we're going to need that. The mass of this droplet is 1.02 times 10 to the negative 11. And the number of these electrons is 4.0 times 10 to the 9. And the charge on an electron, and we'll ignore the sign, is 1.6 times 10 to the 19, I think. Minus 19, yes. I always get them confused, the mass of the electron and the charge on the electron. I think it's that. I'll just check. Yes, it is that. Good memory. Is there anything else we need? So we know the... Oh, go away. We know the initial velocity, that's 0, and we're trying to find the final velocity. Okay. So we're going to need to combine the work done by the electric field and it converts it to kinetic energy. Yeah, kinetic energy, I guess. Okay, so in order to do that, we need to work out the whole Q. And my pen is playing silly with me today. Yep, that's better. So Q is going to be this number of electrons times the charge on the electron. And it's going to be 4.00 times 10 to the 9 times 1.6 times 10 to the minus 19. And I'm not going to worry about this is the negative for now, because it's just the absolute charge we're worried about. It's going from negative to positive, so if we put in negative in, it may even mess us up later on when we take square roots, I think. So 4.0 10 to the 9th, 4.0 10 to the 9th times 1.6 times 10 to the minus 19 is 6.4 times 10 to the power of negative 10. It's going to be QV, and that's going to equal 2mv squared, isn't it? Where m is this m up here. All right, so we can work this out. So let's work this left hand side out. QV 6.4 times 10 to the minus 10 times 4,000. Grab your calculator. 256 to the power of negative 6 times 10 to the minus 6. Okay. And MV, half M. So 1.02 negative 11 times 0.5, 5.1 times 10 to the negative 12. Okay, so V squared is going to be those two divided by each other. So 2.56 times 10 to the negative 6 over 5.1 times 10 to the negative 12. So this is the big negative down the bottom is going to become a positive at the top. So let's work that out. 6 divided by 5.1 E minus 12, 501,960. And let's go 2 decimal places just because we can. So V is going to be the square root of that. So taking the square root is the same thing as raising to the power of a half. So 708.49. And the unit is going to be meters per second. So why didn't I take gravity into account? Well, electromagnetic force is way, way, way stronger than gravity. And when we have something like 4,000 volts, 1 millimeter apart, it's going to overpower the power of gravity by millions. So it wouldn't have made any change to our velocity up until about the 3rd or 4th decimal place. So we can afford to ignore gravity for now. This next question is a kind of take on the Millikan oil drop experiment, except with ink. So if the bottom plate here is positively charged, the top one here must be negatively charged. Okay, what are the forces that are keeping this thing still? It's an equilibrium, so the net forces must equal 0. Well, there's a force pulling it down, which is the weight force, which is mg, the mass, and then it must be equal to and opposite to the electric force, which is EQ. So the weight force, mg, must equal the electric force, which is EQ. So this is a really, really fiendishly clever experiment that was done by a team led by Millikan in the, I think, late 19th, early 20th century. Don't quote me on that one, but they put a charged oil drop and very, very carefully studied these things in magnetic and electrical fields. They knew how much magnitude gravity had, and by finely tuning their instruments until they could notice oil drops standing still, they could work out the charge on an electron or on the dot. So it's very, very fiendishly clever. He wasn't a very nice guy, Millikan, by all accounts, but very, very fiendish experiment. Now, what charge must this have? Well, if the bottom is positive and the top is negative, like sort of reacts to like, it wants to push it away. So the charge itself must be positive, because like repels like. That's the word that I'm looking for. Like repels like, and it's attracted to difference. So this thing wants to go up, but gravity is saying not so fast, and it's pushing it down, pulling it down, and they equal up. They're in equilibrium. They're in kinetic equilibrium. Okay. Question 2, circuits. A air fryer consists of a heating element, 2 lamps, 2 fans, and a lamp. In the diagram below, the heating element is represented by a rheostat. That's that thing there, rheostat, a variable resistor, and 2 identical fans are in series with each other, and the whole circuit is in parallel branches. Okay. Yes. Initially, switch A, which is that one there, is closed, but B is left open. So the fans, whatever they are, the fans is the same. Calculate the current in the lamp. The lamp is that thing there. Okay. We can do that. So using, for some reason my pink little bits there aren't coming off. Using Ohm's law, V equals IR. The voltage is the same everywhere. So 240 volts equals the current going through it times 1000. So the current is going to be 240 divided by 1000, which is 0.24 amps. I think things still haven't gone, but that's how you do that one. It's just algebra, really. Now we're asked to use physics principles to explain what adjustment would need to be made to the rheostat's resistance to increase the power outage of the element. So for this one, I'm going to just go straight to algebra, and I'm going to combine Ohm's law with the power law. Okay, so what I'm going to do is I'm going to combine both of these. Now, I don't want the current in there. I want to know what's going to be the change of power given a change in resistance, and resistance isn't in this one. So what I'm going to do, I'm going to make I the subject here. So I'm going to divide both sides by R. So V divided by R equals the current. So therefore I'm going to put this thing here where I have current times V, and I'm going to end up with this fairly familiar equation there. So the power is voltage squared over R. So because R is downstairs in the denominator, when that goes down, the power goes up. There is a temptation to use this one here that would tend to kind of imply that as the resistance goes up, the power goes down, but this I squared bit ruins that. If you reduce the resistance, the power would stay the same and the current would increase. So I guess it makes sense mathematically, but not in reality. So this next question asks us to prove that the resistance is 32 ohms on this rheostat if it's set to 1800 watts, so power. Remember, the answer is always more power, or more torque. Both switches are now closed. Okay, so everything's done there. Right, so we've got the voltage. The voltage is 240. We've got the power, and that's 1800. We need something that's going to give us something that's going to link power, voltage, and resistance. Okay. So we'll presume that we'll make out that we don't know resistance. So if you were sort of paying attention in the past, I combined two equations, the power equation and Ohm's law. And this one here, I made I the subject. It's V over R times V, which is V squared over R. And that gives us what we're looking for. So if voltage is 240 squared over 32, does that give us 1800? Well, there's only one way to find out. So 240 square is that. Divide that by 32 and we get 1800. And the only way we could get 1800 was if the resistance was 32. So yes, and the resistor and the rheostat, would you draw a rheostat, equals 32 ohms QED. Then now we're asked to calculate the number of coulombs that are produced by this power source, looks like a battery, electrical cells, over the course of 5 minutes. So 5 minutes is not an SI unit. Seconds are the SI unit, so the number of seconds will be 5 times 60, which is 300 seconds. So T will be 300. And according to the tables, the amount of charge is the current times the time. And the current we don't know, but the time we do know is 300. So let's work out the current for each. So the lamp, the light, we know it's 1,000 ohms, and we worked this out before, didn't we? So therefore has 0.24 amps, just looking up a bit, yeah, 0.24 amps. Okay, so we know that has 1800 watts of power, and we know that power is current times the voltage, and we know that the voltage is the same everywhere, and a parallel circuit is 240, so therefore the current going through the rheostat is going to be 1800 divided by 240. I don't know what that is off the top of my head. So 1800 divided by 240, 7.5 amps. Could be more than that, but 7.5 amps. And the fans combined. So the fans combined, there's two of them, 480 ohms, which is 960 ohms combined, because they're in series with each other. You're in parallel circuit, but they're in series with each other. And for that we can use Ohm's law. So the voltage V equals IR, where the voltage is 240. So let me move that up a bit. 240 equals the current that's going through them. The current that goes through one must go through the other one, times 960. So therefore the current going through the resistors is going to be 240 divided by 960. Calculator time again. 240 divided by 960 is 0.25 again. Well, 0.24 up here and 0.25 of those. Yeah, and that's for both. So that's the current that's going through there. So the total current, the total of all of the currents, is going to be 7.5 amps plus 0.24 amps plus 0.25 amps. And I don't know what that is on my calculator. So it's 1 off 0.25, so it's going to be 7.99 amps. Now, coming back to our formula, Q equals IT. So the total charge is 7.99 amps times 300 seconds. It's going to give us a number. 7.99 times 300. 2397. Okay, 2397 watt. Well, it's charge, so it's going to be coulomb. Big C. Alright, so now we're told that unfortunately the lamp stops working. Oh dear. Use physics principles to explain the effect the lamp not working would have on the current in the circuit and the power output of the element. Right, so the effect on the current, there is 0.24 amps going through that lamp, and that's gone. And that's it. So before it was, what, 7.99 99 amps were going through it. Now there is 7.75 amps going through it. And the reason why is that the change in the voltage is 0, and the resistance, change in the resistance in the other resistors is 0, and the resistance of the lamp really equals infinity, so therefore no current goes through it. It's essentially now just a gap. So long story short, the total current will go down in the circuit. Now the effect on power in the element, and it's a bit of a trick question. So the change in power is going to be 0, so the power is still going to be 1800 watts, and the voltage, because they're in parallel, is going to be 240, and there is no change in the resistance, so the resistance is whatever we said it was before, 35 ohms. So the power is going to be the same, because the power is the voltage squared over the resistance, and that's going to stay 1800. The current is not in this equation, and it doesn't matter anyway because they're in parallel circuits. These stay the same because they're in parallel, because parallel, I never get to spell that. 2 L's in the middle, 2 parallel lines in the middle, parallel. So this last question is about magnets. A current carrying wire is placed between the poles of a horseshoe magnet so that the current crosses the magnetic field at right angles. It's perpendicular. This creates a force on the wire shown. Which of the poles labelled A and B in the diagram are the north pole? Okay, so for this we're going to need to use Fleming's left-hand rule. Okay, so we need to work out, is the current coming into or out of the page? Well, that says that it's going into the page. Imagine looking at the back of an arrow as it's being fired. That is going in, is coming out of the page. So it is definitely that one. So it's going into the page. So we take our left hand, we point it in the direction that it's going, so that our thumb is in the same direction as the force. So it's going to want to pull this thing up here, and where we slap is the direction of the magnetic field. So the direction is going to be going there because we slap in that direction, and charge comes from north, so A is north. Again, we put our thumb, so it's in the left hand, so the force is pointing in the same place as our finger. It's going into the page, so then where we slap is the direction of the magnetic force. So A is north. And that's all I can do, unfortunately. The rest of this exam is redacted. I can't see the diagram, and this link doesn't work. And all of these require you to be able to view the diagram. And if it's redacted, not much use. So that's all I can do. So hopefully you enjoyed that. If not, oh well, bad luck, I guess.